products. These two cars, they are all from Germany, and they are just off shelf, available from their website. The core of the diagnostic system is a Vertex 6 FPGA as the processor. Yeah. The 10-channel 3 GHz input signals are first mixed with the 2.95 GHz local oscillator continuous waveform from the local oscillator to generate a 50 MHz intermediate frequency. Then digitized by the 10-channel analog to digital converters running at 125 MHz and transported to the FPGA for digital processing. The diagnostic system is available to provide a high performance with phase resolution less than 0.1 degree and amplitude resolution less than 0.1% full scale. The last but not least application is the FOFB, and also the recently just added enhanced orbit diagnostic in one system on chip. Synchrotron beam stability is a crucial parameter for the third generation light source in order to achieve their optimum performance. Submicro stability is now a common requirement for vertical beam precision. To reach such performance, a global fast optic feedback system are mandatory. An FPGA-based fast optic feedback system has been developed and deployed, and the Australia synchrotron aims to improve the stability of the electron beam. With the FOFB system, it's able to achieve the integrated RMS motion by 50% to 90% up to 300 Hz. The enhanced orbit diagnostic feature is still under development, short as the EOD. Yeah. It will provide the unique features of continuous measurement of the character to position response matrix in real-time mode. With the EOD feature, 5 output signal types are available. First is the traditional fast optic feedback correction data, and second is the wide Gaussian noise stream. Third is their superposition of FOFB and wide Gaussian noise. Fourth is the sinusoidal stream, and last is the combination of FOFB and sinusoidal stream. Okay, as a summary, it is not that difficult to select what processor type to use in your device. You just need to know the key features and the applications. CPU engineering cost is lowest. So if there is no need to use an accelerator, then use the CPU. When it is necessary to get a boost of speed for some feature, check first if it is possible to apply GPU. It might be faster than the CPU, and the engineering effort might be a reasonable compromise. This is especially true if you can apply some of the ready-made GPU libraries. As a last resort, consider the FPGA. There are things you just cannot do with GPU. Immediate high latency processing of data from a special hardware interface, and real-time reactions based on the received data. FPGA is meant for those cases when CPU and GPU is just not enough. Just remember, it is completely okay to spread the work to all of these processing elements. For example, let the FPGA to carry over the front end of the data pipeline, while GPU to handle the later phases, and CPU to control the overall system. The recent semiconductor industry has already provided several new compute architectures which delivers the scalar processors such as CPU and vector processors such as GPU tightly coupled to FPGA. They provide memory mapped access to all three processors. This tightly coupled hybrid architecture allows more dramatic customization and performance increase than any one implementation alone. Okay, that's my presentation.
Thank you, Simon.
Any questions?
We've got time for a question.
I actually have one comment to Simon.
Yes.
It's just that for the from my experience with FPGA and GPU,
Yes.
actually you need to account for engineering costs, of course, but in fact one of the biggest deciding factors is actually power. It's actually power consumption.
Yes.
Yeah. And
I haven't. It's limited by time. I didn't show up the power consumption compared between GPU and FPGA in the same paper I shown before. They have on their paper they have similar scale. So this is not a big problem. But even after optimization with the latest technology, even if FPGA is not much worse than GPU.
Yeah. From my experience, that FPGA actually is more superior in power consumption and for the speed of computation, and also in large scale implementation. Actually, FPGA is cost saving when it comes to cooling. Yeah.
Yes. As I show in the FFT example, in the extremely large scale application, FPGA is better than GPU. But for this middle scale range, maybe GPU is better. Depends on the application.
Agree. Yeah.
Okay, Terry, quick question.
What programming environment do you use with developing?
For FPGA?
Yeah.
You mean? Okay. Yes. Now the latest one is I use the Xilinx FPGA, so I use their Vivado and IDE. They just one software is enough.
Does that allow you to program in C or a high level language?
Yes. Now the Vivado, the latest one, it is the Vivado high level synthesis capability. You can even program it with C type language. It is a subset of C. You can convert C to the VHDL and then finally to the binary code to be config FPGA. Latest one, they just as in the last slide I show is merged the hybrid architecture with CPU and FPGA both. So even in one, the latest IDE is called VITIS, VITIS. It is also a hybrid architecture both for FPGA and CPU. You can develop the FPGA first and then switch to CPU. They can have interaction. All of these interfaces can be easily defined and easily programmed.
Okay, sorry guys, we have to press on. We have a fair bit of program to go through still today.
Yeah.
Yeah, thanks Simon again for the presentation.
Yeah, my pleasure.
Okay, so the next one up, I'm the next one actually, again. So I'll talk about, there we go. Give me a second. Alrighty. So you're seeing, I'm assuming my presentation, right?
We can see it. Or I can see it.
Okay, yeah. So I'll be talking about the PV archiving and the Australian synchrotron. Just as a quick overview, I'll first touch on our previous setup, and then our current setup and the archiving paradigm that we have implemented. And I think that will be pretty much it. Okay, so like I said, I'll first touch on the on the previous archiving paradigm. Since the facility was commissioned, I think we had 2 channel access archivers. So one was for all of the beamlines, and the other one was for the machine. So this gave us a bit of separation between the 2 in case something goes wrong on one. But as I don't know if you are familiar with it, but there was a lot of maintenance with the old archiver. Quite some XML configuration had to be done. And after that was set up correctly, the archiver's engine would pick up the new config every night, and then start archiving or stop archiving a few PVs. So there was quite some input from controls engineers required. As you can see the snippet on the right, this is what's required to archive 2 PVs. So it was generally 5 lines of XML. There were some tools around, I think, to automatically do this, but weren't really used that much. And then every time we added some new functionality, the question was like, what to archive so that there's not too much overhead and we're archiving things and putting time into creating the XML, and then we never look at it and how we should do it. Should it be like a 2-second period, a monitor or scan, and what should we do? So this usually led to not a lot of PVs being archived, and almost as a rule, the PVs would never be taken out of this file if they no longer existed. So obviously there was a bit of a room for improvement there. One of the other drawbacks with the previous archiver was that we would only have a certain amount of data to be able to be retrieved. This was configurable, so if you wanted to access data from 5 years ago, you could run a script that would index all of that. It would take a while, but you could do it. But by default, I think that there was a limit on maybe a few years or so. I'm not sure, maybe Andy can comment on this a bit later on. The old archiver had no support for PV access, which wasn't amazing with the new epics kicking around. We only had 2 hosts, so if that went down, like all of the beamlines or the entire machine went down, I mean not the machine, but the archiving for it went down. No one, I think, with a possible exception of Andy, really knew how it works. It's a bit of a mystery to me, and we had it done semi-automatically, which was nice, but it was it's a bit confusing. And we thought that with the new beamlines on the horizon, we might as well try something new, and also adding a lot of PVs in manually would be a big task on our controls engineers, who are really busy with the important stuff anyway. So we decided to give Archiver Appliance a go. So here's a quick sales pitch, I think, that Slack is trying to sell. When you look at their website, they're aiming to, they're saying that you should be able to archive millions of PVs. And PV access, that was a big thing for us to be ready for the future. Easy scaling as well. And I'll touch on that a bit later on. And you can, it's really easy to retrieve the data from the Archiver Appliance. And you can use a lot of different languages and different approaches, so it's easy for everyone to get to it. And it comes with a bit of a web page for administration and stuff, which the old one didn't come with. And you can actually integrate the old archivers into the new one, so that you have access to the previous data, which for us would be like 12 or 15 years of it, which is something that you obviously don't want to lose. In terms of storage, the way it's done, it has 3 different parts where you can store your data. it kind of makes sense because you can use different technologies for different storages. So for the data that's accessed the most, you want to maybe use something that's a bit more expensive but faster, like maybe memory, like RAM. For long-term storage, which isn't accessed that often, you can maybe save that on a network drive or something like that. So it gives you a bit of flexibility in that way. But users don't have to worry about this. So this is up to the admin to set up, and users don't know where it's coming from. In terms of how the application is running, it's using Tomcat, so it has 4 containers for each archiver appliance, and then MySQL database that holds some basic configuration stuff in it, like how often we archive a certain PV and the names of PVs and stuff like that. And for the actual storage of the data itself, it's using protocol buffers, which is saved on the disk, or where you defined one of the 3 storages to be. So this clustering, this is what they meant by being able to scale up. You have, if you look at this, this is one archiver appliance, and you can have many of them, and then combine them into, like through a load balancer, into a single entry point. So basically, the users can request data via one URL, let's say, and in the back you can have whatever you want going and spread things around so that everything runs smoothly. And you can write your own rules and say, I don't know, this is RF stuff, save this on this appliance, and this is vacuum stuff, save it on this appliance. So basically, you have the freedom to spread the love around however you see fit. Retrieval is done in a few different ways, but it's generally just like it's an HTTP request, and then you specify which format you want the data to be returned in. So here are the few possible formats, and you can do some post-processing on that if you want, like plot binning and stuff like that, or limit the amount of points you're getting back. So that's kind of nice. So this is just a quick example on their website of the amount of code that you need to get to plot something from the archiver. It is Python 2, so maybe yeah, it needs an update, but it demonstrates that you need a few imports and 6 lines of code, which is pretty good. So about the web page for each archiver appliance comes with a few different options to look at. You can look at each PV and a few stats for the PVs. You can look at reports. At reports, like by top 100 events or what's being archived the most. So this one's really good if you see that something's taking a lot of space. We found a few PVs in our case. If you see that something's taking a lot of space, you look at this and you go top 100 PVs by I don't know, space or whatever. And then we found a few waveforms that we didn't know were being archived that would be taking a few gigs. So it's pretty handy. You get some metrics for each appliance, so a PV count and just some interesting stuff. Some storage information and some graphs about how your containers are doing. It comes with a basic data viewer if you want to use on the website directly. It's not the most powerful thing, but it's relatively easy to just see the data if you want to. Okay, so at the synchrotron, what we decided to go with, because you have many options to configure it, is that we decided not to go with any kind of clustering because we don't really have that many PVs that we're archiving. But we decided to go with one appliance per operational area. So operational area is either one of the beamlines, or it can be like integration lab. We have one for integration lab for testing, or the machine. We went with RAM disk storage for the first 4 hours, which is the most heavily accessed usually, and is always the fastest. And then the medium is for next week is just local disk, which is still relatively quick. and everything else. Once it gets older than 7 days, we copy it to the network storage. And for the clients, we have our in-house developed EpicSQT. So we wrote a plugin that basically talks to the archiver. So it's, well, for us and for whoever's using EpicSQT, it should be pretty easy to use. You just have to install protocol buffers. In terms of ownership of this, our group, our team, kind of owns this to some extent. So we set it up for Beamlines and maintain it and rescale it and stuff like that. Keep an eye on it, keep it updated. But it's up to controls engineers for each Beamline to take care of the contents. So they should make sure that everything's set up in the way that things get archived properly. And here is where the archiving paradigm kicks in. So we're thinking, if we're adopting this new technology, and the problem with the old one was that there was a lot of manual fiddling with files to get everything going. That would be really good if we could just automatically archive pretty much everything that makes sense to archive, and then pause everything that hasn't been around for a while. But also we wanted to be able to give users, which would be in this case most likely controls engineers, the ability to add extra stuff that doesn't get picked up automatically, or say this is a PV that I don't want, or archive this in some different way or something like that. So this was the goal at the beginning, and this is what came out. So with the help of our platform management that I talked about earlier, we set up a bunch of a few scripts and a few cron jobs. So we have on each host, we have a cron job that runs every half an hour, and sings the DBL files. So these are the files that contain PV names from all of the IOCs that run on that host. It will sing those files to a predetermined destination. And then the archiver, basically what it does, again every 30 minutes, but it's shifted by 50, so it's like every 30 minutes with a 15-minute offset. It picks up those files and just does a few sanity checks on them. It says, is it archived? If it isn't, edit. Is it of the right type? If it isn't, don't edit, and stuff like that. So basically, they ended up being archived automatically. So some of the things that we don't archive are these records, because usually they don't make a lot of sense and people wouldn't look at them. The reason we don't archive waveforms is mainly because, well, people don't look at them too often, but even if they wanted to, we don't have a nice way in our EpicSQT yet to retrieve or to present the waveform data that's retrieved from the archiver. But anyway, if for whatever reason they want to archive any of this that gets filtered out automatically, they have a way of doing this. So we have a blacklist and a whitelist. So these are two separate files, which are again at specified locations, so archivers know where to look for them, and they are version controlled. So in case of blacklist, controls engineer can say, this is the PV that I don't want archived, even though that PV would normally get archived. And we support some regular expressions so that they don't have to type 17 different PVs in, or 100, but they can just use the regular expressions for that. And then they save it to our version control software, and then archiver just syncs it every time before it runs the script, and it goes, okay, I would normally add that, but it's in the blacklist, so I'm not going to. And similar to that, we have a whitelist where you can add stuff or override the way the archiver would normally archive stuff. And it's again a file that gets regularly updated, and the archiver will just sync it from the version control software. So again, if you want to pause or resume, host doesn't really do much, but the archiver says, like once a day, basically, it runs and says, oh, has this been off for a certain amount of time? If we haven't had anything from this PV, I'll just pause it. We never remove everything really. So once a day we check for that, and then we pause it, and every half an hour we say, oh, is this maybe back that's been paused before? And if it is back, we resume it. So yeah, in terms of how you have to set up your host to sync the DBL files, which contain PV names. Like I said before, this is all done for you during the platform management, or during the host creation using our platform management process. The only thing that you really have to pay attention to is that you have the things mounted that we're expecting to be there, and that in each IOC that's running, you have that call at the end where you basically run the DBL command in the IOC shell, and you save the output of that in the correct location. But again, we have a script that creates IOCs for you. So if you use that script, then you get that for free. And that's it. Any questions?
Are you in contact with anyone at Slack that's associated with the development? Do we?
Yeah, I mean, I am when we have issues.
Okay.
Yeah.
So is it still? I know it's been version 0.0.1 forever, but is it still actively being developed, right?
Oh yeah, definitely it is. I'm not sure what's the deal with the versions, but it is actively being developed, and the guy. What's his name? Morale, I think, or something like that. He's really good. He replies on email really quickly. If you have an issue, you send him a few files over. He has a look at it. He has a lot of diagnostic tools as a place, and he's really keen to help you out.
And he gave a talk at the recent X collaboration meeting. I had a bit of a quick look at that last night. So he's still very active.
Yeah.
I can't speak for the Beamlines, but we did this on the machine. The transition was pretty seamless. It worked very well for us. The retrieval times are heaps lot better. And although we had a bit more of an automated system on the machine to generate these XML config files, quite often the operators or the physicists would say, "Can you archive this PV, please?" And so we could do it, but now we archive virtually most sensible PVs automatically, and haven't had a request to archive stuff since. So it's panned out really well.
Yeah, I mean we're not that advanced yet, but I mean we find the back end is good, just works. The GUI for the user's point of view, I mean that web-based front end is, the new versions has some quirks. But yeah, as you said, for retrieving data, for analysis, whatever, for scripts and stuff, it's
I did a little script to retrieve data in Python, and it was pretty easy in the end. And it works pretty well. It's pretty snappy. And
I've done it in MATLAB and Python as well. Yeah, so
just in terms of numbers, I think with the old system, we were archiving about 35,000 PVs on the machine, and we're now up to about 105,000 approximately. So I'll probably look it up if anyone's really interested, but that's the exact number.
Yeah.
And that's about 105,000 out of about 175,000 altogether on the machine.
Okay.
That's good.
Yeah, I think that's it. So in terms of presentations, we are finished for today. Thank you everybody who presented and everybody who asked questions.
Can I just say thank you, Andreas and David, for organizing this so well, especially being a virtual conference?
Yeah, no worries. We do have one more thing to do, Andy, so we're not done yet.
Okay, well, I'll
just
jump
the presentations are done,
Okay.
but now we're moving into the final phase, which is an open discussion. So we have an hour for that. It was meant to be a guided open discussion with some questions sent in before time. So we have five topics that we can potentially touch on, and we have Carl, who has kindly decided to agreed to join us to maybe help with the first question, which was from ANU, and it's about the SF6 handling and loss control. So maybe if someone from ANU can expand on this a little bit more.
Okay. Okay, so I prepared a few slides.
Great.
Are you ready? Okay, I share screen. Okay, so we start as of 6. I share screen. Can you see it?
Yeah.
Yeah.
Okay. Can you hear me?
Yes.
Normal.
Yes.
It's not like Helium. It's not like SF6.
No, it's pretty good. It's in the middle.
In the middle. All right. Okay, so laser pointer. So SF6. So just to give you background initial, so about SF6. So humans, they made a lot of kind of man-made gases recently in the last few decades. So actually here you see these graphs which indicates the concentration in particle per million. Yes. And basically in atmosphere, measured in atmosphere. So on the left graph here, we've got some gases which actually believed to contribute into the ozone depletion layer plus heating of atmosphere. And on the right side, we've got gases which contribute to global warming. So here you can see our beautiful SF6. So basically things measurements started in 95. So we've got steadily increase of this concentration. Right now it's believed to be about 10 particles per million. So, and also remember, this is logarithmic scale. So it's even much worse than you can see. So certainly this gas is accumulated. Lifetime in the atmosphere is about 3,000 years. So it's a very kind of long-lived gas. So this is why it's very important to basically be very careful. So a few facts about SF6, just as a primer. So in appreciation that it's quite bad gas, in Europe it's banned as a tracer gas in all applications except high voltage switch gear in the electrical industry. Also quite interesting that in 2013, United States Department of Energy identified quite big leaks at laboratories like Princeton Plasma Physics. It was used as a high voltage insulator. And basically they were able to cut annual leaks by 16 tons per annum. So, and this was done by comparing purchases with inventory, assuming the difference was leaked, and then locating and fix the leaks. So it's really serious, and in big laboratories, it's quite considerable. So what's the application? About 10,000 tons produced each year. So over 8 tons used as a dielectric medium in the electrical industry, high voltage breakers, etc. So another uses as inert gas for casting magnesium and inert filling for insulated glazing windows, by the way. Probably it's already banned from this kind of applications. So also it's commonly encountered as a high voltage dielectric in our beautiful Pelletron accelerators. For example, 14 ED at Hive, we've got about 22 tons of this gas. So probably another kind of applications at lower scale. So we've got a semiconductor industry like etch tent. So loudspeakers, because high electric strength and molecular weight. So till 2006, it was used to fill Nike airbags with all the shoes, believe it or not. So when you breathe SF6, it causes voice to become significantly deeper. So it's also used as a magic as invisible water. So you can actually see like light foil boat can be floated in a tank filled with SF6. So also it's classified as mild anesthetic. So certainly it's like this one, just you search on YouTube and you can find few videos like one when this light foil floating on SF6. It's very interesting. So here at ANU, because this was big interest from Synchrotron, we've got big plant. We'll talk a bit later. I'll describe very quickly. But this is very nice recovery unit, which can be used to actually to deal with SF6 at a small scale. Recently, we helped electron microscope unit to actually remove SF6 and store it from this 300 kilovolt power supply from electron microscope. By the way, we keep this high pressure vessel in our lab now. It has got 300 kilovolt feed through, and it can be filled with SF6 up to 6 atmosphere. So we can use it to test electrical equipment, our tubes, etc., with SF6 atmosphere. By the way, you can also use it for leak helium testing when you actually put equipment inside and at high pressure and pressurized with helium as well. So this is quite interesting application. Here, when John Buckwicknell retired recently, we gifted him this little aluminum vessel filled with SF6. No, I'm joking. This is just basically kind of mock-up. All right, so at highest scale, we've got SF6 plant here at Hive, and it's very old plant. This is compressor. And recently, Alan Cooper, he just discovered that we need a little bit to maintain this compressor by changing some sealants inside. So it will be a big exercise, actually dismantle, changing some surfaces, plastics to actually to extend its life by another 100 years, maybe, no, maybe 10, 20 years. So it will be another big exercise. So now, reduction of emission of SF6 right now becomes very important. Few years ago, the cost of 1 kilogram was up to $650 Australian. Then with Trump administration was down to $25, $30 as it was before. And in future, it's not clear, probably it will be again very high cost. So this is why we should be very serious, like a small scale at Synchrotron, but very large scale at ANU at Lucas Heights. So, and here there is some kind of common sense kind of points we can look at when we look at policies, protocols, and operating procedures with SF6. So it's something should be done in all our laboratories to manage SF6 consumption, management, storage, and so. And it includes gas inventory, counting, tracking procedure system. So we can monitor all activities of SF6 like purchases and cylinders, rentals, recycling, and disposals. So management of SF6 acquisition gas inventory. So this consolidates storage inventory and select single vendor or maybe maximize gas utilization from each cylinder. Like maybe pumping out the SF6 and refilling the backfill with other gases. Of course, this should include training. It's not only confined space, but also high pressure gas and raise awareness of emissions and environmental impacts and health impacts of SF6 and byproducts. Because we should remember that during operation and accelerator, we also produce some kind of breakdown products and could be some toxic components. Always ask ourselves question, what we've got is deposit, tiny deposits which left on the surfaces when we enter the tank. So it's not maybe trivial and should be also important. So recycling SF6 gas. So we need utilities to capture use gas in all quantities, any quantity, and then we don't allow when to atmosphere these gases. So we can continue. Certainly leak detection repair is kind of a big attribute of SF6 kind of things like leak detection, like it's soap and using bagging or using halogen leak detectors. So monitoring programs like leak detection teams. So when we do this on a regular basis, a visual inspection to check for any leaks and also gas pressure in components, in storage vessel, in main vessels, and so, etc. And also leak repair. So when you found a leak, so then you need gaskets, new gaskets as well, lubricants or whatever you applied, including large, big scale systems, like we did repair on our vessel, like about 1 meter O-ring. It was leaking for a few years. It was big exercise actually to replace these gaskets. We also should look at equipment upgrade and replacement. So a systematic approach to identifying, anticipating equipment replacement and repair needs, which can reduce overall emission over the time. And of course, we should also look at proper decommissioning. So at the end of life, all the SF6 equipment should be properly decommissioned to avoid emissions. Like we've done this with electron microscope at AME. So we help them to remove this SF6 into our cylinder, which we will reuse in our systems. So I think probably I put here quite few items to consider to actually look. So probably it might be enough information for discussion. So do you see this actually, by the way, do you see this? Probably I'm not sharing screen right now. Okay, I'm just trying to share screen, this screen. Can you see it?
Yeah.
Okay, so basically this is how this vessel aquarium with these girls is, they fill it with SF6 through this continuous filling with SF6 through these holes, and they will demonstrate how this boat is actually floating in this SF6. Now they fill this boat with SF6 and it's kind of sunk. Okay. So basically, this was demonstration of SF6. I'm surprised they still allowed to actually provide emission of the SF6 so easily, even in this kind of exercise. All right, guys. So this was my primer for SF6, and open for any other discussions.
Yeah, thanks, Nikolai. Well, obviously SF6 is a bit of an issue for us too. And actually, I think when I was speaking to, I think, Brian down at the synchrotron there, I think he said there was some kind of reporting aspect which was based on percentage. And from what I understood in the RS system, they had some tiny minuscule amount, but because of any particular loss, which only needed to be tiny, they had to do major reporting. Whereas I know for us, like, I mean, I think at once we lost up to 300 kilograms of the worst one we had, which we were unable to kind of see, which came about because we'd been into the tank so many times, we kept on kind of topping it up, so we didn't really kind of see the release so much, and we ended up building another system which now kind of keeps track of all our inventory, hopefully the entire time. And also after that other leak, we had to, Michael Mann ended up, I think, tracking down, and we got another system which has been installed in 53, which kind of keeps on breathing in the air and the environment and looking for the concentration levels to go up to try to give us notification if we do have any particular leaks to the SF6.
Yeah, David's right. Michael Mann installed quite a good sniffing system that's in the trenches underneath our accelerators in the plant room. We do regular checks of the flanges with the handheld halogen detector, inventory checks, because we're quite heavily regulated, but it also finds these very gradual leaks that end up being many kilograms and forcing us to do reporting and whatnot.
Yeah, actually, the other thing is I'm not sure if it was the Teflon seals or if Teflon has a slow flow or something, but it does look like that we do have to keep on frequently going back and checking all the feed throughs, because you do seem to develop a leak without any real potential notice. I don't know if that's the sealing material just kind of softens over time for some of the seals that came with our system. This is on Sirius and Vega, but yeah, we've certainly had to kind of keep ducking back in to fix things.
It's a lot of those thread sealant paste type things that eventually spring leaks, the ones that were installed by NEC themselves. And both Sirius and Vega are only, 5 or 6 years old, so you would think they would last a lot longer, but we're finding that they require regular intervention and maintenance.
Nicola, hello?
Yeah.
Yeah, Nikolai has actually shown all the aspects in regard to SF6, and just to briefly explain us the situation we have here, we have a tiny amount of SF6. We're talking about 1.5 kilograms for the LINAC waveguide as an isolation gas, and on top of it we have a few SF6 high voltage circuit breaker or high voltage switches. Now, we were forced by ANSTO to follow the procedures. That means what Nikolai said, we have to capture the SF6 professionally, following the Australian rules, using the right bottles, correctly labeled, and the equipment, and therefore we didn't have the right equipment, so we had to outsource everything, which is a major cost factor nowadays, considering the works and the amount of loss we have. Now, what Nikolai also said is, when you look about the total world production of SF6, 8,000 tons a year is actually related to SF6 high voltage switchgear. And what's important here now is when you read the specification that high voltage switchgear is allowed to have a leakage rate of 1% per annum. You always lose SF6, and when you think about this in regard to 8,000 tons, that's a hell of a lot of loss. Now, when I see the gaskets you are using in ANU, you're talking about O-rings and the like, compared to what the SF6 does, SF6 high voltage switchgear, properly sealed, but and also our waveguide, which is using high standard Lille flanges, that is special flange that was developed by CERN to achieve pressures in the order of -8, -10 millibar. So there's hardly any leakage left. So ANU may need to reconsider in the future how they can avoid the leakage. And maybe you should see once in terms of percentage how much you have to top up your system. For us, I was calculating it. We're talking here about the Australian synchrotron, basically about a few grams or less than 10 grams per annum, which is basically nothing. However, we have a prepared procedure to be sure that we can trace it. And the key thing is you could see the model, what was this GRU4, a recovery unit, which is in the order of $30,000-$40,000. That's how you can capture it. But then we realized when we called the contractors, they couldn't pump it down enough. So they had to bring another pump. to bring it down to about 1 millibar to ensure when you calculate the pressure all the way down to 1 millibar to ensure we can extract so much. So we're having less than 1% left. So you need to be sure that how you can trace it. The easiest way to monitor SF6 is not necessarily leakage, again, depending on the system. It's more about that you would actually measure the pressure, and then also when you fill and extract the gas, that you basically weight the bottles, so before and after, and that gives you probably the easiest and most accurate understanding how your situation looks like. That's from my point.
Okay, Carl, it's certainly you're saying very sensible things in regards to the O-rings. So basically, in many places we already replaced all these O-rings with some compounds, also including epoxy compounds, specifically designed for high pressure vessel, because remember, our system is already built in 70s.
Yeah.
And already kind of all these seal surfaces, you can't easily modify or make it better, you know, in most cases. So with these compounds, we actually managed to improve it. So in regards to O-ring, I'm talking about just only one large O-ring, which is basically is installed in the big flange at the top of the machine. And once again, the same O-ring, it's very difficult to change configuration geometry of this flange. It's huge. It's like a big flange, about 1.5 meter diameter. And basically, this O-ring, we just refurbished this O-ring after 50 years in operation. So and now it doesn't leak, like it's not big leak. So remember, the machine is huge. There are many feed-throughs, small feed-throughs in the acceleration tubes. There are many kind of joints, multiple joints, 100 joints between ceramic of the tubes, between tubes, aluminum, O-rings, gaskets, feed-throughs in the turbo pumps, and so, etc., etc. So this is why it makes it so complicated, the entire system, right? It's big, very big, large scale. Regarding pumping, it's even kind of, David mentions that when we pump the machine, when we open the tank, so anytime, like once every 6 months, you have to enter the machine. So you need to pump all SF6 out. And after you pump SF6 out, you need to pump the vessel to raise a good vacuum. But the best we can achieve with our vacuum pump is about 250 micron pressure. So this is what's left of inventory of SF6 after you pump with your vacuum pump. And typically it's about 10 kilogram of SF6 left inside the tank. You can't do any better. Probably you can keep pump running for another month, but it's not practical. Good
we
practical
found the same, Nikolai, with all our vessels at CAS. We find that, sorry, I beg your pardon, what a good time for the phone to ring. We find that the movement of the gas is when we lose it, or when we enter each vessel, there's many kilograms left in because you can't reach ultimate vacuum in there. The vessels do leak statically or when they're just operating, but not as much as when you enter in or moving gas through the different compressors that have different shaft seals of this, that, and the other. Michael Mann recently discovered that our almost brand new plant had a pre-purge circuit on one of the pumps that was allowing a leak of atmospheric gas into our SF6 circuit, which has created other problems. So there's a leak the other way now, and that throws off our calculations of our masses because now we've got partial pressures of all these different atmospheric gases. Very convoluted and complicated system, this. There's no silver bullet.
That's right.
Exactly, and at the end of the day, you have to be reasonable. And what I said before about high voltage switchgear, the key leakage worldwide is related to this high voltage switchgear. We're talking about 8,000 tons per annum compared to a few milligrams we have here. But the interesting thing again for us was when we were bombarded by ANSTO about how important this is, and there was a misunderstanding. They made a calculation error by a factor of 1,000, and instead of 1.5 kilogram, once of a sudden they told us we have 240 tons of SF6, and that's why the alarm bells were ringing at Lucas Heights. So we could fix these, and then things started to become more normal. But what was interesting is we also checked for leaks. We found a small leak beforehand. We had to pump it up to every year by 100 millibars, which is not big. But again, nowadays, when you look about the pressure, it stays stable. And for you guys, in terms of reporting, you need to find out the way how you can report to figure out actually how much SF6 you lose per annum. And that can be a difficult part. As I mentioned before, for us, it's easiest. The easiest way is to measure before and after the SF6 bottle, and that gives you a clear indication how much it is, instead of calculating the volume and the pressure and then come up to a result. Calculating a volume can be very difficult and time intensive to do so compared to just measuring. Another thing is then when I try to figure out actually what are the real specifications in regard to loss in SF6, and here I realized as well that the specifications being given didn't make necessarily sense. So for example, ANSTO stated, as they always want to be better than the rest of the world, the leakage per annum shall be 0.87. And when you read under Merlin-Chorin high voltage switchgear, where they specify that actually the leakage rate is 1% per annum. So you need to be reasonable again.
Carl, I think, in fact, when I was investigating this issue a few years ago, so according to some kind of regulation document, it was in fact 0.5% considered to be default rate. What does it mean? It's not clear. Probably if you're below this default rate and 0.5% of your inventory, which means for your system, it could be grams. For our system, it becomes kilograms. So in this case, for our inventory at ANU, it's like about 50 kilograms per year. It's considered to be default rate. Of course, you want to be as low as possible.
Yes.
So measurement, yes, very tricky, because it's not easy to measure precisely our vessel or our inventory. Like it's huge vessel, how you measure its weight?
Yeah, I was going to say, I think
cylinder, right? It's, you transfer this amount from one big vessel to another.
Yeah, I was going to say, I think when we filled up Sirius, it was about 50 G-size cylinders, individual cylinders that went into filling that up in the beginning. I remember that was a very painful job, talking about tedious tasks. But also to put it in perspective too, so that 300 kilograms that we kind of embarrassingly lost, that worked out to, I think, one coal-fired power plant running for 8 hours a day. Was for the one day kind of things. It was the kind of impact of what that 300 kilograms. So yeah, I think this is where the losses for particularly for the tandem accelerators, probably orders of magnitude of ongoing problems as opposed to the amount which it might be in the RF systems.
Yeah, it's nothing here, but like I said, I was asked to calculate the volume. And like when you have a high voltage switchgear, for example, you don't know how it looks like because the manufacturer doesn't tell you that it's their property. And for you guys to calculate this is also very challenging. And that's why I said the easiest way is when you pump down the system once and you bring it down to a certain vacuum, then you can assume this is 0 now. And then when you fill it up, you measure bottle by bottle and see at the end how many kilograms you pumped in. And then with the pressure, if you want, with the pressure and the molecular mass and temperature, you could actually calculate how much the volume is. Much easier.
Yeah. Carl, what we do, because just to clarify, so we report our losses on annual basis to some kind of a new greens. It looks like this is basically, it's not really a very serious organization. It's a new greens, it's just kind of initiative group. It's not really official or government or whatever. It's just a local organization. They just interested and they ask us to report how much gas we lose every year. So what we do, we measure our inventory once per year under similar conditions, because the volume of our vessel, we just consider it to be constant. So we measure at the same time of the year, and we measure under the same condition, and condition should be accelerator. When we measure pressure in the tank, we run, make sure that accelerator is in operation for at least 24 hours, which means chains are running and voltage is at around 14 megavolt. And this is very important because when you run accelerator at full voltage, so you deposit at least into SF6 gas about few kilowatts from motors, chain motors, and about couple kilowatts from the just heating up resistors, voltage gradient resistors. So after 24 hours, you reach more or less equilibrium, and you do this kind of measurement during August, like, because in August, we've also got kind of some kind of settled temperature in Canberra, like you have similar kind of ambient temperature. So this is why it's very rough, but at least it's consistent. So, and based on this measurement, we measure kind of average pressure and average kilogram or inventory in the system. In the past, we actually approached this annual greens asking to contribute 50,000 to buy, to purchase precise kind of weights. So at least we can measure the weight of the inventory when we pump it into the storage vessel. But you really need highly precision kind of piezo or some kind of system to measure this as well, because we are talking about kilograms, like precision should be few kilograms. So you can measure like 50 kilograms, for instance, lost inventory. But it never happened, so we just keep going. So we count precisely how much gas we inject into this, how much gas we buy or inject or add to inventory on annual basis, and just do the simulation calculation and a brief estimate. But it's not high precision.
Nikolai, so Andrew Downs here from Lucas Science. So we have a temperature and pressure monitoring, and then so that's continuous, and then we actually have some software that uses those values to give us a live mass value. You're right, temperature changes, turn the chains on and off, changes the numbers for sure. Like a 0.2 degree change in temperature on a accelerator the size of yours or Antares can make a big difference in the gas. The calculation's not exact, so, but it does. Yeah, we get a live readout, which gets us within maybe 10 kilograms, I reckon. So that's pretty good.
It's not
bad. But that's the point. If you have a temperature and the pressure, that's sufficient to do the measurement at any time. So you don't necessarily need to go back to a similar condition.
That is kind of correct, but the problem is if the gas doesn't all warm up the same, or one part's hotter than the other, or there's a slight variation, like a 0.2 degree change in temperature can change the mass significantly. So there's always reading errors and accuracy errors on your your thermocouple's all got an RTD in there, so it's close, but it's not spot on.
Yeah, accuracy of thermocouple, temperature distribution around accelerator, like it's tank 30 meters apart. Probably you measure, Andrew, you measure temperature in few spots, in couple spots. At the bottom, at the top of tank, probably not one spot.
Just one.
Well, we only do the calculation from one spot, but we can measure it from other spots. Sometimes it's different, sometimes it's the same. It's not really, it just depends on how long the chains have been running for, air temperature, all that kind of stuff.
It's also near the skin of the tank, so it's not completely representative of the entire vessel.
Yeah, what you may need to do here is in terms of accuracy to calculate how much your error is, and you can include this to your data you will provide. Again, 8,000 tons for high voltage switchgear compared to the amount we are using or you are using, and the accuracy you can achieve, I think this is more than sufficient. What the government is happy for to understand, and also seeing the approach you're doing to further improve it and actually be actively monitoring it. The worst case for you probably would be that you have a leakage and that would not be detected and you would lose all the SF6.
Yeah, that's right. So
yeah.
There you go, Nikolai.
Yeah, you go, Andrew. Go.
Okay, so yeah, I was going to say, this definitely does show us leakage of, we can see 10, 15 kilograms, which is significantly less than what we have to, our trigger level to actually report it. We do report it all, but it is pretty good. And Nicholas mentioned earlier too, that we do have a monitor that sniffs the air around all the accelerators. That's actually that will pick up leaks, but they need to be still pretty big. It's never picked up a real leak on an accelerator before the mass calculation has, because it can see it over a long period, whereas a small leak over a long period, the air disperses before the sensor would pick it up.
Yeah, because Carl, in our accelerators, we also have valves, main valves. Let's say in 14UD, we've got 2 ball valves at the low energy end, at high energy end, right on the neck of the vessel. So basically, in case of leak into the vacuum, let's say ceramic, broken ceramic or something, so this valve will act and stop any leakage into the external leak, like big accidental leak. And the rest, kind of risk assessment, you think that all these metal bits and pieces, kind of all gaskets, you don't expect suddenly big leak happening. So
that's an interesting aspect what you said, just in terms of how we say safety. And that was another issue I had with ANSTO, that the waveguide section, what actually it is, whether or not that should be considered as a piped gas system, or that it's actually a high pressure vessels. And you see once it becomes a piping system which actually transport the gas from one place to the other, then comes an amount of specification given by ANSTO. I said to them, no, what we are doing here is the same and should be treated the same as high voltage switchgear. It is an isolation gas, the same as for you, and it's not that we transport it, and that means there would be different requirements again. So we could avoid.
You could apply for an exemption of some sort if that's possible?
Yeah, look, there's a whole document from ANSTO which specifies what's it called, F6988 piped gas system assessment and design checklist. So you have to go through these things. So for example, when you design something, that you have to identify every single component which is part of this system. And with this, then you have to have the proper documentation in place about in terms of what kind of pressure it can handle, etc., etc., etc. So that can be a nightmare to produce compared to us. And I finally could prove it that actually, yes, It is the same purpose as a high voltage switchgear. It is basically a chamber and not a transport media with valves, etc. in our case, and therefore we did not have to go along this track. Otherwise, I would still writing reports.
So can you remind us what's the actual pressure, operation pressure of your waveguide?
Well, the pressure we can achieve here is we're talking about 10 bars or so, so that's not a problem for it. And as I said, we use these high-tech Lille flanges. These are basically knives which pressure a copper gasket, which go into copper bucket. This is what you use for ultra-high vacuum. It is not compared what you said before an O-ring. So that brings it all the way up to a much higher level. And I assume this is the same way as you deal with vacuum chambers for SF6. This is a confined area, and it's not the house where you have pipes, connections, and the gas flows from here to there. And of course, that's when all these extra requirements come in place.
Sorry, I'm gonna have to jump in here. We had an hour booked to this and spent 40 minutes on 1 out of 5 topics. So maybe I think we've identified who are the people who should be in contact about the SF6. So if you guys maybe want to take it offline, if there are any questions, because we should probably address some of the topics that Kaz proposed for this session.
Sure.
Okay. Thank you, Carl, for joining in.
You're welcome. So if you, Nikolai, what I can do is I can send you once the document the reporter wrote about our SF and where the issues are. It gives you maybe a little bit an idea, and as well the how is the procedure we're following now.
All right. Thank you.
You're welcome. Okay. Thank you very much, and have a lovely weekend, especially in Melbourne with a long weekend. We have horse races in place.
Wonderful.
Yes.
Goodbye.
Okay, bye, Carl.
Bye.
Okay, we've got 10-15 minutes left. So Dave, you proposed 2 topics. One was about network security and segregation methods, and the other one was cheap platforms such as Raspberry Pi and stuff like that. We've kind of touched on a little bit before. So which one do you want to go with?
Well, I was going to say we probably touched on both of them a little bit. I mean, probably the network security. Otherwise, the other one I thought we could be interesting to touch on. I'd be interested to learn people's opinions on the when you're presented with the option of either incorporating, say, like an analog signal into a control system at the interface level, or you have access to, so like the RS-232 output of a device, like say like a vacuum gauge. If there's any preference in which people try to build the systems, whether they try to measure the main signal directly, or if there's an option to use an interface, if there's a tendency to always use the interface, or is it kind of a qualified situation where you just work out how reliable hopefully each thing is?
I think certainly the synchrotron we've tended to use, in fact I think we solely used the RS-232 or similar interface to our vacuum gauges and our ion pumps. I know from the safety system there's a relay you can define, and that's like a hard signal signal into our PLCs. But otherwise we use a device driver, could be a stream device driver, talk to the device to get the value,
right? Rather
than try to input the voltage directly. I mean, it makes it very easy with MOXes and the like. It's just on the network, and the IOC can then be virtualized.
From my experience on one of the beamlines, they had a pump where it had both options, and without a consultation, the decision was made to use the analog signal, and go through like patch panels and stuff like that, get it into PLC, and then from that we read out the I think we're reading the frequency of the fan, which was fine. And on the pump you can set a few things that you want output on that one output, but the problem is because you can only get one, whereas if they went the other way with using the serial channel, which was an option, you can read many different things at one time.
Absolutely.
So that's kind of, I don't know. And I think for pumps, it's usually not something that our equipment protection system would monitor or react on. It basically usually monitors, I think, pressures rather than pumps. So I don't think there's really a need as far as I have experienced.
So you sort of touched on like so the richness of actually more information. Is that something that you just kind of tap into a bit more, or is that you just sort of find you're only really after pressure and that's it? Ignore all the other details from gauges. I mean, it doesn't have to be a vacuum gauge, by the way. It can be other devices as well.
Yeah. You might get a status if it's wrong, whereas if you read in the analog signal, if it goes wrong, it might get up to 0, but 0 might itself be a sane or legal value. And is that 0 because it's broken, or 0 because the value just happens to be 0?
Yeah, oh, that's true. Yeah, I didn't think of that side of it as well.
Also for things like, I know that for vacuum pumps, what they would be interested in sometimes is as just like as a measure that the pump is wearing out. You could see that in order to have the same speed of the fan, it would be pulling more current. So that's something they would look at and want to have archived, and then look over time if that's changing, and if it's like it's indicating that it should be repaired, something like that.
Sorry, is that something you already actively do, or is that like proposed?
That's that was for one of the beam lines, and it kind of, they would like to do it, but it's not done yet. The pump, like the interface of the pump will give you that information if you plug it in via the serial port.
Yeah, I mean, I must admit, I had wondered about some of these kind of advanced maintenance kind of wear indicators and things like that for what's kind of connected. Yeah. Cool. Yeah, but I mean, if there's nothing else on that one, yeah, I guess the that network security one was something that we're sort of still trying to work through. I mean, I think at the moment, looking at the structures I think you guys had in place down there, it looked like most stuff is broken off down into subnets to try to keep everything fairly isolated, and most of the controls is obviously separated from most of the corporate networks and everything.
Absolutely. So the corporate network's definitely different to the controls network, and I think that's good on a number of levels. I mean, not just security, but stops someone inadvertently writing to a PV and buggering things up. And we isolate the beam lines, so each beam line, they can read each other's PVs through our gateways, but they can't. Normally, they just can't interfere with each other, deliberately or inadvertently.
Yeah, so and how does that work for everyone working on the systems? Like, because you got devices which are all sort of sitting on one network, and you might have your offices and that sort of set up on another network.
Well,
how do you manage that?
The SSH port, well, certainly for the machine and the beam lines, the SSH port is open. So if it's a physical or virtual machine or even a container, you can SSH to it and do your stuff. Bandwidth's big enough, you can run your favorite graphical editor if you want to edit a file. Some of the tools you need are on the machine itself.
Yeah, I think that works for engineers, but for scientists, I know that, so for the infrared beamline here, they usually monitor things from their offices, but office is like more of a corporate network, so they can't control it necessarily. But what they do is they have VNC set up. So for that, if they want to control it as well, they just basically log in via VNC and they can control it to that. For now, I think that might get taken away by IT at some stage.
Absolutely, yeah.
I think they want to lock that down.
So I wanted to chime in here by saying that there is supposed to be a major project by IT in defining what ScienceNet is, and that includes, you know, all of our instrument networks, and the interconnectivity between those networks is kind of that's off the table at the moment. But the basic patterns that we use for security and for OS management and all that sort of stuff, it's supposed to be supplied by them as well as the infrastructure. So, so rather than us as sort of hacker type sysadmins trying to do something that, you know, pros are supposed to be doing, the idea is for them to set up all of those things, including all of the security requirements and everything, but then throw it past us and the scientists so that they get everybody on board to try to, you know, come up with a reasonable way of doing all of the things that we've struggled with all these years. And hopefully then provide us with the sysadmin support so that we don't have to look after it. That's the grand plan. We'll see if that actually happens. But by saying that, when we're approached by the project managers that are going to look after this from IT, we should try and provide some level of, well, firstly, to try and help them as much as possible and not be too cagey with them, and treat them with too much suspicion. So I think, you know, we can come up with a sort of a reasonable interplay with those people to get a good outcome.
I will say, actually, we found, I've noticed anyway, a big, massive change in, the posture of IT services now. Like in the past, I think we used to ask them about something and everything would be a security issue. Can't do this. So why, I guess, security issue? Whereas now they seem much more proactive in trying to come up with a way to give you either what you want or something better or similar. And I know when in some of our discussions, they've certainly put a few other ideas on the table we hadn't thought of, which have actually been much better outcomes for us.
Yeah, so they certainly recognise that we are user-facing facilities that are trying to, you know, connect to the outside world. And I think what is very encouraging is Nick Howarth's diagram, which basically shows that all of our instruments are in the low security category. So they're not too worried about the stuff that we have because there's not terribly much in terms of, you know, embarrassing the government or, you know, loss of secrets or, you know, potential damage to radioactive materials and all that sort of stuff that is really high on their agenda. So we're kind of, you know, you can basically do what you want. It's not such a big deal.
This also comes back to the point about you asking, what should I use? Serial? Should I use Ethernet? Should I use RS485? A lot of these devices that have this interconnectivity, who monitors the firmware on those? Who assesses the firmware on those? And I think that's why IT are a bit more cautious these days, especially with that the brand of IP cameras that came with malware for free.
Yeah, I think there was was it Axis camera service or something? They all had to be updated or something.
So there are considerations, and look, I've had heaps of issues just trying to get other than the normal office user permissions on bits of equipment. But I think we need to come to the table with a plan, and they can say, yeah, that's a good idea, or no, it doesn't quite work there, and give their professional solutions. Because if we just say, we've got this, can you help us? They'll go, oh, and sort of, here's a standard out-of-the-box solution. We've got to be an active participant.
Yeah, I think, I mean, I agree with that because we had a recent crackdown on the firewalls on our hosts, which as a rule we just turned off usually, because, well, they get in the way of a lot of things, to be honest. But we were encouraged to change that and to have firewalls turned on, sorry, So we were approached by IT, and they helped us with our platform management stuff, and they prepared a few scripts, Python scripts for us that now dynamically open ports for if you have different, like multiple IOCs running on the host and stuff like that. So it's basically this collaboration working together. They do their own network firewall kind of thing, and we tell them what we need from them to get it going on our side, and now everything's automatic, and they're happy and we're happy. So it is a bit of that, I think.
Actually, Nikolai and Peter probably. I was talking with Richard Kitchen, who, for people who don't know, he's probably the main architect of ExcelNet, and I know he mentioned that trying to get into the ANU system now, he has to use some two-factor authentication process as well. But I'm just kind of curious if you guys had any more fallout locally after, I think there was the breach of all the student stuff at ANU there a while ago.
Yeah, I mean, they've upped the security. We've changed our VPN, but fundamentally, we've been unaffected, really. The only thing is they've come down hard on the number of connections per port. So we have to think about how many ports are available for devices. We can't just keep daisy chaining them and just keep connecting switches to switches to switches. But really, yeah, just apart from a few vendor changes, you could say, nothing much has changed. But yeah, our control network is a separate network from the departmental network. And I think same as Andrew, I SSH in and pretty much do everything from my departmental networked desk computer through SSH, and it's all fine.
Yeah. And we've got rules. Not the general office network can't SSH into the machine network. You have to be on the controls engineer's office network, as it were, to be able to SSH in. So it's a little bit more, it's not just anyone can SSH in. You know.
No, it's similar with us too. Like, as in, the departmental network is separate from other networks within the research school. So it's a smaller group. So it ends up being a smaller group of people.
Okay, we are out of time for today, which leaves a few topics that we haven't really talked about, unfortunately. But that's a good encouragement for maybe meeting again, I guess.
Yep.
So I just wanted to really quickly just say thank you for everyone for joining in. Big thanks to all of the presenters. This obviously wouldn't be possible without you, so yeah, thanks for that. Special thanks to David, Nikolai, and Peter for helping to organize this. Also to Andrew, who held the all-day EPICS training yesterday, which was probably quite hard to do. I don't know, I've never delivered an 8-hour training. So
my voice throat was a little tender last night. So
yeah, not surprised.
I rested it today.
Yeah. Also, thank you to Rosemary and Andreas, for setting up the ASCII stuff so that we could deliver the training, and Rosemary for helping out with all the registrations and finding people and helping them up with their accounts. An award for the most active participant goes to Terry, as per usual. Well done, Terry. Expected nothing less. Yeah, so basically, from what I've heard today, it seems like we're all doing a lot of really great work around the facilities here in Australia. It seems that there are a lot of different equipment around, different machines, with different techniques. But we seem, it's my opinion, that we were kind of solving a lot of similar problems in the end, although they are on different machines. So things that came up today, I think, there was a lot of talk of standardization, testing, factory acceptance testing, even remote factory acceptance testing. What the COVID impact was on projects and on facilities, how we do archiving, how we comply with regulators, and also cybersecurity, which seems to be a bit of a weak spot for most of the facilities here today. So, and just to include Nick in this a little bit, as he said, and I really like that, back in the day, each facility was kind of doing their own thing. They were all working on different solutions to the same problem. But now I think, and like he said, in the days where everything's online, everything's on Git, and it's just so easy to catch up everywhere, and you can fly to Sydney for, I don't know, $200 if you go with Tiger Air. Probably not around anymore anyway, but it's relatively cheap to meet. I don't think there is really a good reason for us not to collaborate a bit more. And I think meetings like this are a perfect opportunity for that. I have to say that I learned a lot about other facilities today. I will be in touch with some of the presenters due to because of the materials that they presented. And none of that would be possible, or it would be extremely hard or unlikely to happen if we didn't have a platform to do this. And I think like collaboration meetings like this are a good platform to maybe plant, I don't know, to plant a seed and get some collaborations going. So from few discussions with David and Nikolai as well, we kind of agreed that it would be nice to have this more often. Maybe do it every 6 months, maybe do it once a year. It depends on you know, we can just kind of figure it out. But I think we all agree that it was it's a really good thing to do, because I don't think we have a similar platform where we can do what we did here today. So yeah, thank you all again for showing, for joining, and hope to see you soon.
Yeah, thank you.
Thank you very much, everybody.
Yeah, and no, particularly, yeah, Andreas, thanks for all your effort in putting in. You definitely did, you know, carried a lot of the heavy lifting on this one, mate, and greatly appreciate it. And likewise, Andy, for going to all the effort of putting a training course. I mean, that was a huge, you know, to all of us, and certainly, I think, really look forward to expanding on some of those things in future. I'd certainly probably want to sit through the training once again, just to kind of reshore things up. And
any questions, do email me or contact me somehow.
Yeah, and I'd really like to see, even if we can sort of take some of these things that have been presented and kind of turn them into a bit of a resource that we can kind of tap into. And maybe that's something we need to have a bit of a talk about, how what would be a good way of possibly doing that too.
Yeah, definitely. I think the like meetings like this are good to, you know, you showcase what you have, what your concerns are, what you're struggling with, and then, you know, there's a quick 5-minute or maybe not even that Q&A session at the end, which is usually not, you don't get everything out of it, but you get an idea and you can follow up with people, and something good can come out, I think.
Okay, so David Button, so about the name, title of this meeting, because we had these 2 meetings in series, like first ATF was first 3 days, and then this is basically, so what do you think? Do we keep it or we change our name, title?
Well, if I can jump, well, David, you can go, you tell me.
Oh, no, that's all right, mate. You've well deserved to jump in.
Okay, I was, well, the ATF was just stealing a bit of thunder, I think, from a bit more recognized forum that was going on, and we were piggybacking on that, but I would like us to to separate and detach and cut the umbilical cord and just go our own way and come up with something more appropriate.
Yeah, I guess
Open for suggestions.
Yeah, I guess it'd be good to kind of work out how broad a scope we want to sort of bring into these kind of discussions. Like certainly that kind of integration space, and like it was good having those kind of talks on about FPGA work and all those various other things as well, which will spill into the control. So it's not just all, you say, EPICS tables and things, but
there's a lot more.
that integration, full kind of integration into instruments and data acquisition and so forth. I'd certainly be keen to hear in this space a bit more.
Yeah. So we can figure out the name, and I'm sure there are a lot of other facilities or universities or, I don't know, CSIRO and stuff like that around Australia who might be interested in joining in this. I know, like the was it the SK, the Pathfinder project?
Yeah.
We're doing a lot of great stuff, and they are actually doing it with EPICS, but they might be someone who we might want to reach out to.
Yeah.
It doesn't have to be necessarily limited to accelerators, and we have Nick here who is kind of not really in the accelerator world as he said. So yeah, I don't think we should limit ourselves.
A lot of the time, these technical forums end up being commandeered by the applications of the technology that we're using. I used to come from the cyclotron space, and whenever I used to go to the cyclotron users group, radio chemists would always come in and steal the show. And I feel that perhaps the ATF might be sometimes going down that path, and we need to get back the technical aspect like we've been talking about now. It's been very nice to just throw ideas out, because we are all the technicians, the technical people on the ground. This is the stuff we should be talking about.
Yeah.
We should keep the name and just mold the timetable a bit better, perhaps.
You think we should keep the name?
Or maybe Australian or Trolls Forum, ACF. Ooh, I'm sure we can come up with something.
Yeah. Well, anyway, I think name is the least of our problems. we can come up with something.
I think you just need to put a prize up, like Tim Tams or something, for the best.
Tim Tams? All right.
Best name?
I'm happy to donate a packet of Tim Tams.
I can donate your favorite box of black.
But we should definitely not just limit it to controls, right?
No, just technical things to
That's
do
right. Yeah.
with this field. Keep AC and S in as well. You're not an accelerator, but you accelerate neutrons from a different source, of course. But that sort of technical stuff that we have in common needs to be talked about, because we've all got individual problems that have a common thread that others may have solved, and it's great. Like Peter, I saw inside your box of tricks, there's the high voltage isolation PCBs. We've tried to do a few things at ANSTO ourselves, blown up some PLC input cards in the process, so things like that we can share. That'd be fantastic.
Yep. We've had issues with some newer generation labeled turbo pumps, so seems like, is anyone else having issues as well?
Oh, yeah, we've got labeled turbo pumps, but I'm not sure if we have any issues with them.
Well,
we can compare notes.
Yeah. We had one blow up and then go away for repair for 9 months and then come back and blow up within 5 seconds. Like, as in catastrophic. Oof.
Fins flying everywhere, sort of thing.
The fins shattered, yeah.
Oh.
But we bought it at a very good discount initially.
That's good.
Off the back of the truck sort of discount, was it?
No, we didn't drop by the synchrotron and pick up the end of life stuff, but
yeah. I mean, obviously like the original ATF was a little bit different to, I think, what took place this year. So we might have to sort of kind of review like what happened in the first part of the week and sort of see how things sort of merge into. And likewise, if you want to kind of break off a bit more specific controls applications kind of theme separately into its own meeting. Yeah.
Yeah, we can definitely discuss it. I think as long as the initiative and the will is there, we'll down.
Yeah, I mean, what used to be good too with the other ATF, because particularly with all the technicians and engineers involved, there's a lot of people who interact with the industry, and that also helps out with sponsorship and stuff as well. Quite often, you know, your local BIFA, maybe Leibold, and various ones are kind of happy to kind of chip in and help out with the running of an actual forum. If it moves to some kind of site location as opposed to just the virtual world that we're in at the moment.
Yep. Okay. Virtual is cheap.
Yes.
Yeah. But it's not the same. It's not the same
It isn't.
as meeting in person, right? And having a chit chat.
Yeah. It's always good to, at the end of the day like this, to go out and have a meal and have all the conversations that we didn't quite get to have in the virtual space.
Mm-hmm. Yeah.
Okay.
Okay.
Anything else, or shall we call it? All right, we'll call it.
Great job. Thank you, guys.
Thank you.
Sorry.
Yeah.
Have a nice weekend.
And you. Bye now.
Okay. See ya.
See ya.
Bye.